Okay. Ben, is that a new hand or a leftover hand? Leftover hand. Okay. So let's just talk about one piece. And I know your brain is still in past project mode, but I do want to get you thinking about one little thing. So we will talk about just some of the math required here. I like this meme. I don't know if you've seen this one, probably so. I like that one. There's a million built on this set of pictures, right? A million memes on that one set of pictures. Okay, so here's the challenge here, right? And we're not going to have time to get it all sorted out, but I want you to think about it. You have hopefully had enough math. You were supposed to have at least geometry, right? You should at least have had some geometry, and you should have had enough geometry to get you to the point where you can answer these questions. But I want you to think just briefly about how we're going to deal with the fact that we're going to draw a center circle, right? We're going to draw this one circle in the center, and that's the starting point for the whole fractal. We're going to then draw children around that. The first child is going to be due north. It's going to be exactly above that center circle. And then all the children are going to be spaced equidistantly. So if you have one child, it's here. If you have two children, they're here and here. If you have three, it's here, here, and here, right? So you're always going to have equidistant children, but the first child is always going to be directly above you. Also, for this moment, we can assume a radius ratio of 50%. In other words, if the parent has a radius of 1, then the child is going to have a radius of 0.5. More likely, this one's going to be, let's say, 100. This one's going to have a radius of 50. Okay. Also, notice that the distance between the tangent point here and the center of the circle is going to be the same as the radius of the parent circle, right? So this distance, D2, is the same as this distance, D1, okay? The question is, having all of those things in place, what do we have to do the math so that we can calculate, for instance, the child's center? So let's just start with a very easy assumption where we say, for instance, let's just make this radius of 1. Let's make this distance 1, right? This is a unit circle for our purposes. And then let's say that we have this child above it. The question is, if this is at 0, 0, right? Let's just assume Cartesian world because that's easier for now. If the center of this circle is at 0, 0, the question is, how do I find the center of the child circle? Anybody remember enough math to help us get going here?
You would just multiply D1 by 2 and add that to the Y.
Okay, and that works only if it's directly above, right? But so that works maybe for one circle, but what about the next child that's now at some other angle?
It's radius times cosine of the angle and then sine.
Right. Okay.
Radius times sine of cosine the other.
That's right. So, yeah. So what we have to know here is when we want to find the x value for the child circle, we're going to have to take the cosine of something or another. And what is that something or another? Right? In math, it's called theta. And what is the number here at this point? What is theta at this? If we're talking about this circle, because now we're talking about radians, right? Not degrees.
Pi/2.
Right. So this is now, right, pi/2, right?
That's going to be 0.
And then what'd you say? Sorry?
That's going to be 0, so.
Right. And then, so for y, we're going to find sine of pi/2, right? So to find, and what does that actually get us? That gets us to here, right? In a unit circle, these two things are going to find the x and y component, or the x and y coordinates of the tangent point that we're interested in. So what do we have to do now to get it to extend up?
Double it.
Multiply by what? Right? going to have to multiply by the radius of the parent, right? Parent radius. Does that make sense? So the geometry of it is that if you take the, to find the x and y values of this tangent point, you're going to take cosine of whatever this theta is. And it turns out that, remember, in polar coordinates, this is 0, right? This is pi. And 0 is also pi over 2. So then, therefore, this is pi over 2, right? This is 3 pi over 2 down here, right? So what you need to do then to start thinking about this math is going to be stuff like this, okay? And you notice that also gives you the tangent point here without the multiplication. So with a little bit of manipulation here, you can find this point, and this point, right? So you now know where the center of the circle is and where those tangent lines need to be drawn, and you know it for any arbitrary theta, right? It doesn't just work for this one where the child is above. As long as you calculate a proper theta, and I would recommend thinking here in radians and not degrees, right? Think about this in polar coordinates. As long as you do that, this math actually starts getting you a long, long way, okay? Then, of course, you can figure out, you know, to spread the children equally, that's going to be 2 times pi, right? 2 times pi divided by the number of children, right? And that's going to yield your theta offset, or your, yeah, whatever you want to call that, right? Your theta offset. So that way, you know, hey, I can figure out how many children I have. Then I'm going to start at pi over 2, but then for the other children, I know I just need to go that offset each time and go around the circle for however many children you have. Does that make sense? The other thing is, once you know this center point, when you go to draw a circle using graphics, you don't draw from its center, you draw from its upper left-hand corner of its bounding box. So how do I find this point, which is the actual point at which you start drawing the circle? What's this distance? What's this distance? Right? Everybody see that? To find the bounding box, you literally just have to go to the left and up by the radius, by the amount of the radius. So finding the bounding box is trivial, right? So a lot of this math really comes out of that beginning little bit. This is geometry brushing up against trigonometry, right? You don't have to have taken trig to use this. Hopefully you did a little bit of this, of polar coordinates and geometry. And just knowing just this little bit about cosine and sine gets you a long way towards the solution, okay? Now, there's a whole other set of problems that we're going to run into, because in the graphics universe, that's not a Cartesian universe. It's not that the big circle is centered at 0, 0. Also, by the way, you know, this thing has a radius of more than that, right? So it's not 1, but it's going to be, you know, 100 or something. So of course, that's why we have to multiply by the radius. It's not, you know, if it were a unit circle, that's enough. But here you've got to multiply to get yourself up there. But that's literally the start of all of the math. And I would suggest that when you're thinking about your graphics, when you're thinking about generating your fractals, you focus on this stuff and stay, number one, think in polar coordinates, think in radians. And number two, think in Cartesian land. Don't think about where it is in graphics and the fact that the y-axis is a little inverted and that the origin is up here in the corner. Like, just erase all that from your brain, because that's just an easy little offset at the end, right? Those are very easy things to take care of at the last minute when you go to draw. So as you're thinking about where you'll generate your stuff and how the math works, I would say stay centered at 0. Don't worry about the graphics land changes. You'll figure that out at the end, etc. Yep. Ben, go ahead.
What do you mean by look at it in terms of polar coordinates and then look in terms of Cartesian?
I'm
'Cause, like,
saying
understand what you mean by that,
I'm
but,
saying think in radians
right.
and think in a world in which your big circle is centered at 0, 0.
Okay. The big circle in terms of fractals would be like the very
This very center of the
very
circle.
center one.
You're
Okay.
always going to start with one circle, and then it's going to have children around it, but it's always right smack in the middle of your display.
And I haven't, I'll be honest, I haven't read the project instructions yet, but we're not like doing any other shapes, right? It's just circles,
It's just circles and lines.
circles and line. Okay.
That's right. But that brings an interesting point up later too, in that in the end, what we're going to want to do, and this is getting a little too detailed, what we're going to want to do is the fractal engine is going to set up all of the math for these things, and it's going to put them all in a list, and then it's going to pass that list when asked to the display, and then the display is going to cause them to draw. So it's literally doing all the fancy math, all the recursion, figuring out where everything goes, packaging that all up as a list of shapes that need to be drawn. And then the display is simply going to make each one of those shapes draw in the appropriate spot. And the offsetting to Cartesian, or sorry, to graphics land can all be done at that point. Like, you don't have to worry about it here. Let the engine focus on figuring out the math. And then at the end, the shape can do its little bit of offset very easily. Okay. All right. All right, so we're about out of time here, but I just want